we're not going to do this an infinite number of times, but you'll see how it's done. Okay, so let's start somewhere. So let's try x is 0. So, and here's your h, right? 0, plus minus 3, plus minus 6, dot, dot, dot. Okay, so x binary operation h will be, so your binary operation here is now just plus. Okay, so it'll be x plus the elements of your subgroup. So it'll be x plus these. And if you add 0 to anything here, you get the same thing. So the xh, when x is 0, is effectively just this, which is h. Okay? So the left coset of xh when x is 0 is just 3z, which is this. It's just this, 3z. Right? Now when x is 1, can you see you're just adding 1 here? You add 1 to each of these numbers. So that's the same thing as 1 plus 3z. I hope you follow that. Right? Now if x is 2, instead of adding 0 here, you're adding 2. So you get 2 here, plus minus 3 plus 2, plus minus 6 plus 2, and so on. Right? Which is just this. So it's 2 plus 3z. Right? Now we've done the sort of particular cases, 0, 1, and 2. Now let's go to the general case. Now, R can be anything, any integer, right? But if R is congruent to 1, mod 3, now if you've forgotten what the definition of congruency between two integers is, go back to earlier lectures. Right? So if R is congruent to 1 mod 3, then if you add this R to this, so you've got an R here now, so that's, where are we? Yeah. So if R is congruent to 0 mod 3, then you're adding effectively plus or minus 3 to h, or plus or minus 6 to h, or plus or minus 9 to h, which is still just 3z. Okay? So if R is congruent to 0, your left coset for RH is just 3z. Alright? Now if R is congruent to 1, similar logic, you'll just get 1 plus 3z. And if R is congruent to 2, mod 3, then the left coset will be 2 plus 3z. Right? So again, here are 3 different cosets, which are the same 3 as here. Okay? So even though this set's infinite, so is this. So we've got an infinite group and an infinite subgroup. The number of different cosets for those infinite group and subgroup is finite. In fact, only 3. Right? That one, that one, that one. So you've got 3 different cosets. Right? Okay, now comes the nitty-gritty. In stepping stone towards proving Lagrange's theorem, we need these results. And it's pretty hefty, tight, logical reason theorem proving. So we'll plunge in, and so it's theorem 46, and it has 3 parts, 1, 2, 3, and each one is an if and only if type statement. So in effect we've got 6 parts. So it'll take a while, but the theory is essential for later steps to prove Lagrange's theorem. This is famous result of finite group theory. All right. Well, as a kind of lead-in, let me. You can start getting curious a bit. Like for this case, you had two different cosets, only 2, even though the order of the group was 6. So say you have like here or here, they're the same coset, right? So but the elements are different. Like this is element A, that's element A squared. So if 2 cosets are the same, like these 2 are the same, right? And these 2 elements are different, But if two cosets are the same, is there some kind of relationship that you can form between these two elements? Now you could ask yourself that question. Right? Be curious. Well, there is. Otherwise, why am I talking about it? And here it is. So if two cosets are equal, even though these elements here are different, right? And that's possible. Like, here's an example. So if these two cosets are the same and the two elements are different, there is some kind of connection between x and y. And here it is. And it's that the inverse x, y belongs to your subgroup. Right? So, and it's an if and only if. So if that's true, that's true. And if that's true, that's true. So we need to prove it both ways because it's a IFF type statement. Right? Now, here's an interesting result. So if x belongs to some coset, let x be A here. It belongs to this coset. Right? So there it is, A. And if B belongs to a coset here, so B belongs to this coset. So so if x belongs to a particular coset, then that coset is xh, right? And we'll prove that both ways. And if two cosets are equal, then and these two elements here are different, then those two elements belong to the same coset. Like, for example, these two cosets are equal, right? And x and y, so like BA and BA squared, they belong to the same coset. Well, they do. See, BA and BA squared. That's this coset, but here it is again, the same coset, BA squared, right? So you may say a bit, so what? But we need these results for for further steps as a stepping stone towards the proof of the famous Lagrange theorem result. All right. Now there's so many steps involved. I'm definitely going to need the textbook because I didn't bother remembering this. All right. So let's do the if. As usual, you start strong convention. Start with the if part when you're trying to prove an IFF type theorem statement. So so the if is you start with this. So we start with this and we have to prove that. Okay, a bit of discussion about proof technique here. So we start with this and we have to show that it's the if part, so from right to left. Remember, we've done this so many times, so I won't go over that again. So how do you prove the left-hand side? Now, this is a coset, right? And so is this. So there's still sets. A coset's still a set. So how do you prove that two sets are equal? Right? So go back to earlier lecture. Now, firstly, so you need the notion of a subset. So if S and T are sets, here's the notion of a subset. This is revision again, right? Just to remind you. So if it's true that for all members of a set S, for any member of set S, if that member, call it X, is also a member of set T, then S must be a subset. Must be a subset of T, right? So if we can show that for any member that is a subset, belongs to S, then it belongs to T, then we know that this set is a subset of this one. S is a subset of T. Okay. Now, how do you prove two sets are equal? By showing one is a subset of the other, and the other is a subset of the one. Right? So S is a subset of T, and T is a subset of S. So that implies they're equal. The only way you can have these two being compatible is if they're equal to each other. S equals T. So to prove, when we go this way from right to left, to prove these two sets equal, we will use this strategy, right? And to derive these two, we will use this strategy. Right? Now we've done this kind of thing a few times, so that's the strategy for proving Theorem 46 Part 1, this part. Okay, now a lot of steps. Now, all right, now so let A, just I could use X, just a random element A, let A belong to X of H, right? Okay, so what I'm trying to do here is, if A belongs to X of H, that's this one, then I need to show that A also belongs to Y of H. And if I can do that, then I know that X of H, and that's true for any element, so therefore X of H would be a subset of Y of H, because I'd have this kind of thing, right? So let's try to do that. So if A belongs to X of H, then you can then A must be of this form. Okay, it must be of that form, because there will be some member, H1, let's say, just of the subgroup H, so that A is equal to it. Right? If that's not clear to you, give it a bit of thought. Right? So A must be of that form. All right. Now we know this. We're given that. We start with the right hand side and prove. Now x minus y, sorry, x inverse y. So we've got that. Okay, therefore x is, and this belongs to H, so it must be one of the H's. So we can write that as just some H. Right? This belongs to H. So this is one of the H's, little h, one of the members of the subgroup H. Right? So you got this. Now you can rewrite this as